My name is Kerinia Cusick, and I'm the board president at Center for Renewables Integration. And today we're going to be talking about a trend outlook for battery storage from 2020 to 2030. I'm going to share my screen in a few minutes and with some content, but first we're going to sort of give you an overview of what we're going to talk about in this presentation. So we're going to hit 4 key issues, which is applications. So talking about applications for battery storage, the technologies, the main technologies that are basically being used right now, cost trends, looking into the future, and then sort of the predominant business models that are being used right now. So there are really sort of 6 primary applications for energy storage, and we'll talk about each one of those a little more. The first, I'll call it just sort of the remote grid application. So this would be a location that's not connected or reached by any transmission or distribution lines, and there is a need for power. So there probably is storage combined with some generation, be it solar, or maybe it could even be storage combined with diesel, although that would be less common. This is an increasingly common model, particularly in locations such as the United States, Australia, India, where you might have occasional power outages. And there's a desire for resiliency. So I'm going to call that a grid-connected resiliency microgrid. And so those could be either commercial, or it could be an industrial application, or it could be a residential application. So examples of types of projects that I've worked on have been anything from an individual homeowner up to an Amazon distribution center in the US and internationally. Work on factory applications in India. The grid is so significant that they need some sort of grid in order to continue to operate. You're also starting to see much more applications for peak shift, what I'll call peak shift solar, where solar is producing most during the middle of the day, and there's a desire to have that producing more when there is great need for electricity, which often is in the evening. So you've seen some applications for that. There's an example in Hawaii that's been talked about a fair amount, where you have the solar plant is shifted to the maximum production is shifted from noon to about 4 o'clock in the afternoon. There are also just standalone applications for energy storage. Those are, I'll call those standalone wholesale applications, where the battery is participating in wholesale markets. And then standalone where the battery is used in lieu of sort of changes that need to be made to increase the transmission or capability of the transmission or the distribution system. So those are sort of 6 broad applications. Keep those in mind, and I'm going to dive into some. I'm going to screen share, and we'll talk about some more details. Get into some of the details. Okay, so here we are screen sharing at this point in time, and attempting to advance the slides. Here we go. So there are the applications I talked about. Here is sort of the snapshot of the 6 different applications we walked through. So now let's dive into some of the details. So even though I talked about the fact that we have 6 sort of primary applications, in reality, almost every battery system is actually a multi-use application. And so we talk about revenue stacking or multi-use a lot in this industry. So this is a little bit of a busy chart, so I will walk you through here. On the right-hand side, I use a company called Lazard. They do a lot of good analysis. Their information is always very current and very detailed. You see an example here from Lazard showing, I think, have some both U.S. and international applications. You've got the California ISO. You've got ERCOT and some other grid operators, major grid operators in the United States. And then you have some examples here, UK and Australia and Germany too as well as Canada. So what all these different color bars are showing you is the fact that really all these revenues stack on top of each other. So a battery is never doing just one thing. In order to be economically viable and in order to really get the greatest benefit out of it, you want it to be doing many things. So you'll see a battery that is doing both energy arbitrage, where it's basically energy arbitrage as you are powering up the battery when electricity prices are very low, and then putting that electricity back out onto the grid when electricity prices are very high. But energy arbitrage in of itself does not really build a battery. A lot of these batteries are really designed to act as capacity assets. And so that would be sort of like those sort of yellow colors there, or sort of the darker colors on the graph on the right. And so whether you call it capacity or resource adequacy or demand response, these are all sort of similar aspects of the same thing, which is the ability for the grid operator to be able to meet the peak power demand. And so usually these can be sort of like peak power demand is usually 1 hour, can be, or something on the order of that. And so these are great applications for batteries where they just sort of have to output all of their power for a relatively short period of time. Another application that you use for batteries, and this is additive, so often a battery that's doing capacity during some peak hours of the day, be that 4 to 6 p.m., is also used at night in order to be able to provide frequency regulation. So frequency set regulation is basically a service that is used to maintain the frequency of the grid at a specific hertz, and that is also compensated. Spinning reserves is another service that you see basically being provided, or transmission and distribution services or deferral. We haven't seen too many examples yet because of regulatory barriers of batteries providing transmission and or distribution deferral, and also participating in markets. So if you look at that chart on the right-hand side, you'll see that usually it's kind of just, if they're doing transmission and distribution, they're just usually one revenue stream. But usually you see that almost all batteries that are being built and deployed are doing multiple things at different hours during the day. So this concept of they're really all, even though they're sort of primarily a wholesale asset or primarily a behind the meter asset, in reality, they're participating in multiple markets and multiple services, which is one of the things that makes it a little bit more complicated. So hopefully that gives you an idea of the applications for battery storage. Let's talk a little bit about the technologies now, which there are sort of 3 primary technologies. Lead acid batteries have been around for a very long time. We now talk in terms of advanced lead acid, which basically means lead acid that doesn't require as much maintenance as the older batteries used to. Lead acid batteries are comparatively cheap. They are great for a limited number of cycles. So if you're going to cycle the battery once a day, that technology does very well for 1 charge cycle, 1 discharge cycle. So for an off-grid application, they're relatively low cost compared to other solutions. The challenge is that nobody really is too excited about these technologies because they're really relatively flat projections as you look forward into the future, the costs are going to be. A lot of people are excited about lithium-ion based technologies, and there are many different kinds of lithium batteries, lithium-ion phosphonate, lithium, titanium. There are so many different kinds, but in general, they're sort of all a very broad category of lithium-ion batteries. The reason that these are the reason people are excited about these batteries is because of the fact that if you look forward to 2030, there's a lot of projections showing the fact that we're anticipating another 50% decrease in prices from 2020, and this is actually following an 85% decrease in prices in the past decade or so. So there's been a dramatic drop in these prices, which is why a lot of people are very focused on these technologies. And they're very good for we're going to be using it to do a lot of. So if you're going to be cycling it 20, 30 times a day, they do best. And so that's why this technology was initially adapted and created really for, or really used primarily in the automotive sector. You also see, of course, in everybody's, laptops and computers, but this is why the technology was translated to the automotive sector, and also why the technology is being also now translated to the connected energy storage applications. So where they're most cost competitive when they're used as capacity assets. So as I mentioned, high power, short duration is where they're really most effective. These batteries are available with good warranties, good performance warranties. Of course, there's a downside to everything, right? So challenges that they're having with this technology is controlling temperature. So often you're finding in very hot applications, it has to be installed with some sort of thermal control, like a ventilation or air conditioning system. A number of fires in 2018, 2019 that they've created the industry to really focus on ensuring the fact that managing the thermal characteristics of the battery effectively. There's a lot of, then I'm going to go to the final category, which I'll call flow batteries, which are usually very big batteries, terrible for automotive applications, but would be very good for grid applications. The challenge is that we're still, we've been waiting on this technology to be fully commercially available. Obviously, there haven't, in the last 5 years, there haven't been a ton of progress made. So I think this would be a good question as we look to trends for the next 10 years. Will flow batteries finally get their breakout moment and become fully commercially available, or do they remain, a technology that never really makes it out of the laboratory? But given how promising they are, still a lot of focus on them. Where they are really good and really designed to be most effective is the fact that they are designed for very long duration discharges. So if you have an application that requires 8 hours of a discharge, they would be excellent for that application. And given the fact that we don't have, full commercial capability for these batteries yet, we don't really know what sort of future cost declines are going to be expected for these. As I said, a lot of people are really focusing on lithium because of the fact that the projected cost declines. We've got in the bottom left-hand side of your chart here is a compilation from the National Renewable Energy Laboratories showing all the different projections for what future costs are going to be for lithium ion. And so those are shown in a gray line, and they've sort of characterized what is a high, and what is a low, and sort of a midpoint. And in rough numbers, sort of looking at the midpoint, by 2030, costs will be approximately 50% less than they are today. So that is sort of, has everybody very focused, continue to focus on this industry. And the reason is really because of scale. I'll talk about that a little bit more in the next slide, but as you get on the right-hand side, what you're seeing here is sort of looking at how all the different components go into the installed cost of a battery system. So you've got some engineering aspects, some design aspects to it. You've got soft costs, which would be everything from sales to the cost for human resources in a company. Balance of system hardware is going to be all the electronics. You may remember that I also mentioned the need for air conditioning system. So those will typically be incorporated into the balance of system. And then the battery pack itself, and they're showing projections for how much those battery pack costs are going to go down. So you're seeing cost declines pretty much across the board, where sort of everything is coming down by about 10%, all the way up to about some being able to get some, like the soft costs down 17%. So that shows you sort of a breakdown. One of the challenges of talking about batteries is the fact that everybody talks in terms of batteries as far as dollars, or sorry, whatever financial term, per kilowatt hour. And this is really an energy term. And so people sort of say, oh, wow, a battery, a lithium ion battery is 30 cents per kilowatt hour. Well, that is so not competitive, cost competitive with current costs today. Because cost of electricity on a wholesale basis is, in the United States, is 3 to 4 cents a kilowatt hour. So 30 cents a kilowatt hour, obviously you look at that and you say it's not cost competitive. It's never going to be cost competitive. Well, once again, the primary application really for batteries, especially lithium ion batteries today, is frequency regulation and capacity, which actually are measured in terms of dollars per kilowatt month or something like that. So, so it's this misnomer of the metric, of cost metric, that makes a lot of people conclude that battery systems are really just not cost competitive. But if you look at, but they are. But if you look at the reasons also then that costs are going to continue to come down, is because of the fact that you've got really manufacturing. And so when I started working in 2013 in energy storage, we, really the big companies that we were dealing with at the time were just Panasonic and Samsung. And so look at the battery, the chart on the right-hand side. And even though we're looking at electric vehicle sales, as I said, the technology is really largely the same. What's going into grid connected lithium ion is largely the same as a automotive lithium ion. And so you've got Panasonic still has a very significant market share, but you've got other companies, you've got BYD, you've got LG Chem, who have entered the market and seeing their respective market share. And all of these companies are dramatically increasing their manufacturing capability. You've got Panasonic on the left-hand side there. You can see a chart that shows Panasonic ramping their capability from approximately 10 gigawatts per year to over 50 gigawatts per year. This was from 2017 to 2020. And you've got, BYD, not quite as dramatic, but all of the companies are basically ramping up capability. And as they ramp up manufacturing capability, you're also getting costs are coming down, and battery density is increasing too as well. So let's talk a little bit about the business models. And frankly, you're seeing a full range of business models. So if an asset is going to be used as a transmission asset or as a distribution asset, typically that's a front of the meter application. So it is not on the customer side of the meter, it's on the utility side of the meter. You're seeing utility ownership is very common in this application, where these are assets that are basically just included in rate base, and the utility gets a rate of return. In the US, certainly, and I don't know about in other countries, there's some regulatory ambiguity on whether rate-based assets can participate in wholesale markets. So this might be an interesting question in other countries to see if it's been resolved. Obviously, the more the asset can be utilized, the more productive it is. Excuse me for a second. In applications where you have a battery participating in wholesale markets, or doing what I call solar shifting, you have two sort of primary business models at that point in time. You've got either a merchant application, which is where it is any other asset participating in the market and it receives the market clearing price, or it might have a contracted service. So potentially it has a contract with utility to provide energy or capacity. And certainly we're seeing a lot of batteries being built under this model at this point in time. Anything that's being built with a merchant model is usually a bit more expensive in order to be able to finance. So it's less attractive, so people try to enter into contracts if they're able to do so. These behind the meter resiliency applications or microgrids, there's two sort of primary business models that you're seeing here. This is where you're seeing, generally you're not going to see utility participating in providing these, but you have seen some examples of that. A savings contract is one common example where there is a commitment to reduce peak demand charges, and the contract is basically a savings contract. You are seeing also applications, as I said, utilities. You don't usually see utilities participating in savings contracts, but you're seeing utilities in some cases participating in offering a lease option to put storage in somebody's home if they want it, or they can, somebody wants or a business wants storage, they can lease it directly from a third party, or they can obviously purchase it themselves. Off-grid applications are generally limited to a lease or a purchase. I would say that that's actually a relatively small percentage of the market. So you're really seeing those other models as being much more dominant at this point in time. So that's sort of an overview of the energy storage at this point. In summary, between 2020 and 2030, you're going to continue to see an absolute explosion of energy storage. You're going to see it's going to be fueled by dramatic cost declines. I think that the 50% cost decline for lithium-based is very realistic because it doesn't rely upon a technology breakthrough. It's just simply a question of increasing manufacturing scale. So that's much more predictable and easier to sort of convince yourself that, yes, I think that those cost declines will absolutely occur. I think as you start to see more cost declines, you will start to see broader applications. So I'm sure in my predictions here of talking about sort of the various trends that I've excluded some that are probably going to emerge that we're not anticipating at this point in time. One example that comes to mind that we haven't really started to see too much of is fleets. So fleet where you have an entire city's bus system and how it's not being used at night. It can be used in order to be combined. Those storage applications could be combined with excess wind, for example, in capturing excess wind when it's being generated and it's very cheap, and then discharging it later in the day. I think that there's also commercial applications. Possibly, there was the news of Amazon investing in 100,000, I think the number was 100,000, I'd have to double check that, on electric vehicles and changing much of their fleet to electric vehicles. That's going to create very interesting opportunities I don't think we fully understand at this point in time. I think the big debate as I look forward to 2030 is whether does flow technology come out of the lab, or does lithium ion continue to dominate the industry? I think probably 5 years ago, I would have predicted the fact that that flow technology does make it out of the lab and beats lithium ion. I think now I would not place the same bet. I think there's a good chance that there's so much advances being done in lithium ion based technology that it continues to be the dominant technology. You'll continue to see increases in density. You'll continue to see increases in charging speed too as well. So a lot of these batteries are still relatively slow to charge. And those charging speeds will continue to go up dramatically as they are able to absorb more power more quickly as they charge. So those are some of my predictions between now and 2030, and looking forward to checking these in 2030 and seeing which ones were right.